So the purpose of this lecture is to figure out what the ratio of the volumes of the cube to a tetrahedron inside the cube and an octahedron inside the cube, to figure out what the ratio of those three are. And I'm going to present this in three very different ways. The first way, I'm going to sort of do a bit of hand waving and just do it very quickly. And then I'm going to do it kind of more the standard way. And then I'm going to do it in a way that I would say is more elegant. I like the term elegant in mathematics. Elegant really meaning beautiful, and beauty in terms of the simplicity of mathematics. So let's go ahead and see what this looks like. We have a cube. Let's focus first on the solid lines inside the cube. That's an octahedron, such that the points of the octahedron are at the centers of each of the faces of the cube. And then we have, with the heavy dotted lines, you can see a tetrahedron. It's a little bit hard to make that out. The edges of the tetrahedron cut across the diagonals of each of the faces of the cube. So here's what I'm going to do. I'm going to start out first to find the volume of the octahedron. Once again, the volume of the octahedron is twice the volume of the pyramid inside of that. I think you'll remember that. And so I'm going to focus on the pyramid once again. But in particular, I'm going to focus on the square going around the outside of the pyramid. So right here. So I ask you this: if I take this square going around the sort of the belt of the octahedron, and I allow that square to fall onto the floor of the cube, can you picture that? I'll say it again. That square of the octahedron is going to fall onto the floor of the cube, and then I'm going to draw that. What is that going to look like? So here it is. So this is that blue belt going around the octahedron. It's fallen onto the floor of the cube. Why did I do that? Because what I want to do is I want to compare the area of the white square to the blue. Can you see? The blue square is how much of the area of the white square? Well, if you imagine drawing in the two diagonals of the blue square, do you see what have I done? I've created 8 small triangles, and the blue square consists of half of them. Therefore, what can I say? I can say that the area of the blue square is exactly half the white square, and the white square is certainly the length of the whole edge of the white square is the edge of the cube, and so it's 1/2 of EC squared. So that was very nice. So let's just use that information. The volume of the pyramid is, of course, always 1/3 area of the base times the height. And what is the area of the base? We just said it's 1/2 EC squared. And what's the height? Do you remember this from before? What's the height of this pyramid? Well, it's 1/2 the edge of the cube. If we multiply all this out, what are we going to get? 1/3 times 1/2 times 1/2 is 1/12 EC cubed. And therefore, what's the volume of the octahedron? The pyramid is 1/12. The volume of the octahedron is 1/6 of EC cubed, which is also meaning 1/6 of the volume of the cube. So again, that tells us that the volume of the cube, the ratio of the volume of the cube, leaving some space eventually for the tetrahedron, the volume of the octahedron is equal to 6 to 1. All right, now let's work with the tetrahedron. This is the big surprise, the moment you've been waiting for and perhaps didn't even know it. Here we go. So this is what I call elegant. Why? Well, I'm going to take the tetrahedron, and from the tetrahedron, I'm going to produce the octahedron. Can you see how that's done? Imagine that the tetrahedron was a piece of wood. And do you see how the octahedron sits inside the tetrahedron? How am I going to take that piece of wood, the tetrahedron, and produce the octahedron? I'm simply going to cut off the corners of the tetrahedron. Do you see that? If I cut off the four corners of the tetrahedron in the right way, I will be left with the octahedron. So let's look at one of those corners. I want to say that this corner down here, I'm going to color that in to be orange. Let's do that right now. I just took the tetrahedron and I chopped off this corner. This pink line here, which is the length of this cut right here, is how much of the whole length of the tetrahedron up here? Well, it's half as long. Why? Well, clearly this point here is the midpoint of the whole edge. This point here is the midpoint of this whole edge. There's something called the triangle midpoint theorem. This must be half of all of that. What shape, by the way, is this orange thing that I just cut off? That shape is also a tetrahedron. It's a similar shape to the original tetrahedron. I just cut off the corner of the tetrahedron, and that orange shape is similar to, it's the exact same shape, and it's exactly half as much. So what can we say if it's half as much? Well, perhaps you know this. I can now say that of these two shapes, the original green tetrahedron and the orange tetrahedron, that the ratio of their linear dimensions is 2 to 1. The ratio of their linear dimensions, what does that mean? It means the edge of the orange one is exactly half the edge of the green one. And if that's true, and this is something we've worked on in class, what must be the ratio of their volumes? What must it be? Well, I'm going to take this and I'm going to cube it. That's what we know. And therefore, the ratio must be 8 to 1. What does that mean? It means that the volume of the orange tetrahedron is 1/8 of the volume of the green tetrahedron. Did you follow that? I take the green tetrahedron and I chopped off the corner. I just chopped off 1/8 of it. And how many corners do I need to cut off? I need to cut off 4 corners. And each time I cut it off, I cut off 1/8. I'm cutting off 4/8 of the tetrahedron to get the octahedron. So what does that mean? I can say, therefore, the tetrahedron has twice the volume of the octahedron. That's the elegant solution. And what does that tell me? That tells me that the volume of the tetrahedron is twice the volume of the octahedron, or what we can say is the ratio of the tetrahedron to the octahedron is 2 to 1. And that was the thing that I was so pleased to have discovered as I was driving in the car to the post office. Tetrahedron to octahedron is 2 to 1. I'm hoping you found that at least a little bit interesting. Thanks for listening. If you made it to the end, if you really held on your hat the whole time, that was impressive because that was tough. But I think trying to really follow something that's difficult really helps to develop your thinking. Thank you. Have a good rest of the day. Bye.